welcome to this session of the class. So, we are basically looking into the various properties of the membrane based systems and various definitions which will be quite useful for the process modeling. So, we have looked into the permeability, we have looked into the retention, we have looked into the osmotic pressure, we have seen how the osmotic pressure of the solution will be really measured and connected to the concentration of the solute into the system, and then how the permeability of the membrane and the retention of the membrane are defined and how they are really connected to the throughput of the process and the selectivity of the membrane. And then we have looked into the definition of the various difference of real retention and observed retention, how they are measured and how they will be can be really measured accurately by conducting a separate set of experiments. Next definition that will be quite important in our case is molecular weight cutoff. So, sometimes you will be seeing this MWCO of the membrane is really very important in order to specify a membrane. Now, in a membrane there cannot be a unimodal pore size, or I should not say unimodal, it should not be a uniform pore sized membrane. That means, membrane cannot have a unique pore size throughout its whole matrix. So, therefore, what will be existing, actually what is existing is that there will be a distribution of pore size that will be existing into the membrane. This is known as pore size distribution or PSD. So, therefore, if you would really look for a membrane, you cannot have a uniform pore size membrane, there will be a distribution of pore size, although one can have an average pore size. So, if you remember that whenever we are discussing about the categories of different membrane based processes, we have specified some pore size of the membrane. Now, this pore size is basically an average pore size of the of the membrane. Now, this average of the pore size is basically obtained by the averaging the pore size distribution. Now, this if you how the pore size distribution is calculated, this will be calculated by measuring the retention versus molecular weight of solutes. Now, if the so what we do, we conduct an experiment by using molecular of several solutes of different molecular weights. For example, but these solutes have to be neutral solutes. For example, an example of neutral solutes is polyethylene glycol. We already mentioned polyethylene glycol during our steps of, whenever we discuss the steps of casting. So, polyethylene glycol is basically a polymer which is a neutral polymer. That is very important. We have to take the neutral polymers, for example, polyethylene glycol, polyvinyl pyrrolidone, etc. And this polyethylene glycol polymer is available with different molecular weights. That means, in market the PEG is available with different molecular weights starting from 200, 400, 600, 1000, 10,000, 20,000, 40,000 Dalton, 1 lakh Dalton, so and so forth. So, we take the different polyethylene glycol of various molecular weight at a particular concentration, prepare a solution, and then we measure, we conduct the experiment in a small scale, small laboratory filtration cell, and measure its permeability. Similarly, we do experiments with different molecular weights of the solutes and measure the retention, and then plot the retention as a function of molecular weight in a log scale. So, this is basically similar scale. This is a log scale in the molecular weight, because you are looking for you are covering a wide molecular weight starting from 200 to 1 lakh, and then this is in a normal scale. Okay. So, if you really do that, then you will be getting an S-shaped curve something like this, where R is 100%. So, as I was talking about, once you generate this retention versus molecular weight curve of the solutes for this particular membrane, I am coming close to whatever I am trying to talk about, the molecular weight cutoff. So, therefore, since there exists a distribution of pore size in a membrane, it is very difficult to measure the pore size distribution. There are instruments for measuring the pore size distribution, for example, porometer and so on and so forth, but this instrument itself will be costing minimum 45 lakhs, 40 to 45 lakhs. So, instrument is very expensive. In fact, some of the research units or the institutions, it is very difficult to procure that instrument. So, it is very difficult to measure the pore size distribution. Even if you measure a pore size distribution, then ultimately you will be talking about, you will be specifying a membrane by its average pore size. So, if you have a pore size distribution which will be ultimately you will be converting to an average pore size, then it is very difficult to identify this particular average pore size membrane will be good for what purpose. So, whether let's say will be landing up with a membrane which will be having an average pore, which will be there will be existing a pore size distribution in this membrane, and we have measured an average pore size of the membrane. Let us say the average pore size is around 40 angstrom or so, or let us say 4 nanometer is 40 angstrom. So, for particular this membrane with average pore size 40 angstrom, this will be used for separation of which solute. It is very difficult to understand that. So, therefore, a concept has come out that instead of pore size, can we just relate that what is the typical molecular weight of the solute, it will be in this for separation of typical molecular weight of solutes, this membrane will be effective. In order to answer this question, the concept of molecular cutoff has come up. So, therefore, how this molecular cutoff will be measured? We generate a curve by measuring the retention of solutes of different molecular weights, but the neutral solutes is very important. We have to select a neutral solute, because otherwise there will be a charge interaction. If we take a protein, there will be proteins who can be charged depending on the pH of the solution and the isoelectric point of the protein. So, there can be charge interaction between the membrane surface and the protein, and actual retention capability of the protein will be of the membrane can be masked. So, in order to avoid that, it is very important to select a neutral solute and measure its concentration, its retention at different molecular weight levels. So, we generate this curve, and the value of molecular weight corresponding to 90% of retention. This value is 90% of retention, and the molecular weight corresponding to that is known as the molecular weight cutoff of the membrane. So, we define molecular weight cutoff of the membrane is that molecule which will be molecule of the solute, which will be molecular weight of the solute, which will be retained by 90% of the membrane. So, this is a typical definition of molecular weight cutoff of the membrane, and from this is a typical method by which molecular cutoff of the membrane is defined. So, therefore, all the membranes are manufactured based on the molecular weight cutoff only, because it is very difficult to get the pore size distribution, average pore size. Even if you get an average pore size, it is very difficult to connect it to its utility in order to separate a particular solute. On the other hand, if you can directly specify this particular membrane is qualified enough to separate this molecular weight of the solute, then it will be very useful. So, therefore, the molecular weight solute is defined, and if molecular weight cutoff of the membrane is 10,000, that means this particular membrane will be retained solutes having molecular weight beyond 10,000. Solutes having molecular weight less than 10,000 Dalton, they will be permeating through the membrane. So, therefore, 10,000 cutoff membrane means it will allow it will retain solutes having molecular weight more than 10,000, and it will permeate solutes which will be having a molecular weight less than 10,000. So, if you go to a manufacturer, he will not supply you the membrane based on its average pore size. he will supply you the membrane based on the molecular cutoff. One has to place an order that I would like to have 10 pieces of 10,000 molecular cutoff, 10 pieces of 1 lakh molecular cutoff, 10 pieces of 10,000 or 2,000 molecular cutoff. So, he will be supplying the material to you. So, what is the molecular cutoff is therefore? Therefore, the molecular cutoff an easy way to represent or quantify the rating of the membrane. And the principle based on this molecular cutoff is defined is that molecularity of the solute is directly proportional to the size of the solute. So, if the size is more, its molecularity is more. So, therefore, in order to separate that, you have to get a larger pore size membrane or larger molecular cutoff membrane. If the size of the solute you would like to separate is less, its molecularity is less. So, you would like to have a molecular cutoff, low molecular cutoff membrane. So, one can identify a particular membrane by looking into the molecularity of the solutes to be separated, and the molecular cutoff value will be helping in identify that particular membrane for that particular purpose or application. Now, if the distribution of retention versus molecular weight is very sharp, then it is called a narrow cutoff membrane. Or because actually the variation is very small, and if it is wide, then this is known as the diffused cutoff membrane. Therefore, it is desirable to have a narrow cutoff membrane in order to have a particular application, but sometimes because of the very complex phenomena involving with the demixing processes, then the narrow cutoff membrane is very difficult to obtain. Most of the cases one land up with the diffused cutoff membrane, and from the molecular cutoff as defined as 90% retention of the solute is an easy way to identify a particular membrane for a particular operation. Okay. So, we have looked into the various applications of the membranes and various properties that will be really looking into the membranes, which will be really useful for our purposes, for our modeling purposes. Now, let us look into the details of the various driving forces of membrane separation processes. The basic transport driving forces of the transport processes is the passive transport. They are categorized under this. In case of passive transport, the chemical potential in the feed stream is more than the chemical potential in the permeate. So, let us say this is the feed or retented stream, and this is the filtrate or the permeate stream. By the way, now in case of a membrane, the feed stream is also called as the retented stream, because that is retained by the membrane, and the filtrate is also known as the permeate stream or permeate side, because that has been permeated by the through the membrane. So, in the feed stream, if the chemical potential of a particular component A is higher than the chemical potential in the downstream, so mu A prime is the chemical potential in the feed, and mu A double prime is the chemical potential in the permeate, and if mu A prime is greater than mu A double prime, then there will be solute transport through the membrane from the feed side to the permeate side, and this is known as the passive transport. Second transport mechanism is known as the facilitated transport. Now, in this case, the transport has been facilitated by an agent that is present within the membrane barrier. So, this is the feed site, this is the permeate site, and you have chemical potential mu A prime of the species A in the feed site, and in the permeate site you are having the chemical potential mu A double prime. But in this case it is not a straight this thing, the solute will be dissolved in the membrane matrix. So, this is the membrane in the membrane matrix, and there is another species B that is present in the membrane matrix. It will be making a complex with the solute. So, A plus B will be giving to A B. So, there will be a species that has been present within this membrane. So, this species will be will be reacting with A, forming a complex A B whenever A is dissolved into the membrane matrix or the polymer matrix. Now, the A B is formed, the complex A B is formed, and A B is not allowed to come out of the membrane either in the feed site or into the permeate site, but A B does not have any concentration in the permeate site. So, therefore, because of the concentration gradient, it will be transported by diffusion through the permeate site, and it facilitates transport of A from the feed site to the permeate site. Then it will be it will be dissociated in this site, and A will be dissolving to the permeate site. So, in this case what is happening, that the agent B is facilitating transport of A from the feed site to the permeate site. Therefore, this process is called the facilitated transport. The third process is known as the active transport of species. In case of active transport, the solute is transported from the feed site to the permeate site by active transport. So, it is being transported against its potential difference. So, chemical potential of A is in the feed site is mu A prime, and that is in permeate site is mu A double prime. So, there will be an agent here who will be again making a complex with A, and then it will be transported, and that will be giving you the activation energy, and this will be transported against the driving force, and then it will be dissolved to the permeate site. So, this active transport is generally occurring in most of the biological systems in physiological system. Most of physiological system we are having the active transport, and in our membrane based processes, whatever we will be covering in this course will be basically getting into the looking into the passive transport and the facilitated transport. Okay. Now, we will be looking into the various relationship between the description of transport processes using the phenomenological equation and description of transport by logical equations. So, the transport of solute through the membrane can be described by the phenomenological equation. Let us first understand what is the phenomenological equation. This is nothing but a natural phenomena which will be arising out of cause effect relationship. If there is a cause in a nature, there will be an effect. If there is a driving force, there is a gradient of driving force existing, that will lead to flux or transport of species. So, the cause is the gradient of the driving force, and the effect is the transport of species. So, this cause effect relationship is known as the phenomenological equation. These are occurring as natural phenomena, and by these phenomenological equations, the the flux is generally, this is mathematically represented as flux is proportional to the driving force. So, they occur in the phenomena, and the proportionality constant is the characteristic property of the system. So, what is the proportionality constant? Constant is basically the system characteristic. Okay. Now, there are several phenomenological equations or physics, similar type of phenomena are happening, and various famous laws are existing to describe this system. So, let us just have a summary of this, which are quite common to us. Phenomena involved, phenomenological relation, flux, driving force, and the proportionality constant we are just talking about. The first one is the Fick's law of mass transport through by diffusion. We are talking about a mass flux. And what is the driving force? Concentration difference or concentration gradient. And what is the corresponding proportionality constant? It is the solute diffusivity. The second one is known as Ohm's law for current. What is the flux? Flux is basically electricity or charge flux. What is the driving force? Potential gradient, electric potential gradient. And what is the proportionality constant? It is basically conductance or inverse of resistance. Okay. The second common thing is, the third common phenomenological equation is Fourier's law of heat conduction. We are talking about the heat flux, thermal heat flux, and what is the driving force? Temperature difference. And thermal conductivity is the proportionality constant. So, these well known three examples are the examples of phenomenological equations or relationship, how a phenomena is related to the driving force. So, the flux is the cause, and the driving force is the cause, and the flux is the effect or the result. And various constants of this cause effect relationship, proportionality constants, are basically related to the various system properties. Similarly, in our membrane based processes also, we are having a volumetric flux or mass flux. If we just convert the volumetric flux by multiplying the density, we will be getting the mass flux, and this volumetric flux or mass flux is generated by the driving force. What is the driving force? In our case, maybe pressure difference may be a driving force. Okay. So, volumetric flux is proportional to delta P if the pressure difference is driving force. These are for the pressure driven membrane based processes, and the proportionality constant is the membrane permeability. So, permeability is the proportionality constant. Sometimes permeability is also related to the resistance of the membrane, hydraulic resistance of the membrane, and this is related to the membrane resistance and sometimes it is also called the hydraulic resistance of the membrane. And it is inversely proportional to the membrane permeability, and mu is the dense viscosity of permeating solution, and typically in most of the cases it is close to the water viscosity 10 to the minus 3 Pascal second. So, if the permeability is measured, or if the permeability is known, the membrane resistance can be evaluated. If membrane resistance is known, then permeability can be evaluated. If you look into the dimension of membrane resistance, if you put the value of dimension of mu, there is a viscosity, it is Pascal second, and permeability is meter by Pascal second, the unit of membrane resistance, hydraulic resistance, will be typically in meter inverse. Okay. So, therefore, in case of membrane based processes, under normal conditions, we have the volumetric flux or the mass flux is the cause or the result, and the pressure gradient is the driving force, and with the proportionality constant is given by the membrane permeability. Similarly, if as we have discussed, in an actual separation process, the gradient of chemical potential is the real driving force, and it will be having a pressure, temperature, and composition. So, any of these can be change in any of these will be causing the flow of the of the flux of the solute. So, if we have a pressure, so in membrane based processes, the driving forces may be interdependent. So, gradient of any of these or many of these or all of these or two of these will be causing a flux of the solute through the membrane. They can be interdependent. Thus, a concentration difference, a concentration gradient across membrane leads to flow of matter, also builds up pressure. The example is osmosis. Pressure difference, pressure gradient across membrane leads to volumetric flow plus concentration difference. This is the reverse osmosis. Temperature difference across membrane or temperature gradient across membrane leads to heat flow plus flow of matter. This is known as thermodiffusion or Sorey effect. And next is concentration difference across membrane. It may cause the mass flux plus temperature gradient. This is known as the Duffer effect. So, therefore, we can see that the general driving force is gradient of chemical potential, which will be having three component: pressure, temperature, and composition. Now, and these driving forces are interdependent. If one of them will change, if two of them will be changed, if three of them will be changed, then there will be cause of flow of matter along with with the temperature difference or also with the pressure difference. That means, in other words, their driving forces are interdependent, and if we have a temperature difference across the membrane, if there is no pressure difference, then also there can be flow of matter or can be separation occur from the feed site to the permeate site. So, this has been understood. The actual driving force of the membrane separation is the gradient of chemical potential, which is a common driving force of any separation process. Now, pressure, temperature, composition will be the independent driving parameters which will be controlling the chemical potential. If any one of them change, if two of them will change, if three of them will change, then they will be causing the flow of matter. And we are assuming that electrochemical potential difference is absent. If that is present, that will be another root cause of change in chemical potential. Okay. So, in this class we have looked into the various differences, various definitions of parameters. Those will be important for our modeling course in membrane separation process, and also the nature of the driving forces, those will be occurring in membrane processes. Thank you very much. In the next class, we will be starting the modeling of reverse osmosis system by defining first what is the difference between the osmosis and reverse osmosis. Thank you very much.